Good morning all of you student. So again welcome to lecture series for TyBsc physics. We have to see here the subject is the solid state physics and we want to continue the first chapter, that is the crystalline state, and we want to continue the point which is the different types of the symmetry, and that symmetry, different symmetry operation we have see here, that is the translational symmetry, rotational symmetry, skew symmetry, again symmetry under mirror reflection, inversion through a point or the center of the symmetry, and glide plane symmetry. So these are the different types of the symmetry which is normally occurs or which is commonly occurs. With that symmetry we want to see so deep point, and we want to start the first point which is the translational symmetry. So now here the symmetry, different types of symmetry. First point we want to see here which is the translational symmetry. Translational symmetry, or you have to know that what is mean by translational symmetry or what is mean by translatory motion. So that motion, that object or that point which is moving to straight line, that is known as the translatory motion, and we want to see here the translatory or translational symmetry, that we can translate the entire crystal structure by translation operation, that is known as the translation symmetry. So that we can translate entire crystal structure by translation operation. So we can translate. What is mean by translation symmetry? That is we can translate entire crystal by translation operation, by translation operation. So this is known as translational symmetry, known as translational symmetry. Okay, so if we consider that is lattice point, that lattice point which is considered is R, and under the translation vector which is the translation vector considered as the T bar, and gives the another vector point, that is vector point is R prime. So that which is the identical condition, that is R prime is equal to R bar plus T bar, and we have to know that translational operator for three-dimensional space system which is given by T is equal to N1 A bar plus N2 B bar plus N2 C bar, that A bar, B bar, C bar which is the translational vector, and N1, N2 and N3 which is given by the integer number. So for example we have to consider that this is the lattice point, crystal point starting from this. Suppose this vector which is considered as the translatory vector, that is considered as T bar, and for example this vector for this point which is considered as the vector which is given by R bar, and that the resultant operator or resultant which is given by for this which is given by vector r bar prime. So that notation or that relation which is given as, or we want to write in the form of, that is r bar prime is equal to vector r bar plus translational operator, that is t bar, which is given by this fashion. And we have to see, for example, in three dimensional space, that t bar which is operator which is given by vector t bar which is translation operator, which is given by t bar is equal to n1 into a bar plus n2 into b bar and plus n3 into c bar. In this relation, that a bar, that b bar and c bar, which is given as the translation vector. So a bar comma b bar comma c bar, which is translational vector, primitive translational vector. Translational vector, and n1 n2 n3, n1 comma n2 comma n3, which is given as the integer number. Okay, so integer number. So this is the deep idea or information about the translatory motion, or we have to know that what is mean by translatory motion, that object which is moving in the translatory or straight line path. So that is known as the translatory motion. And translational symmetry, which is given by, we can translate the entire crystal system into symmetry by the translation operation, that is known as the translational symmetry. We want to see the next symmetry, and next symmetry point which is given as the rotational symmetry. And that rotational symmetry, we have to give an idea that to understand the terms of the rotational symmetry, and that consider n, for example, see for last few minutes ago and last lecture, that is the equilateral triangle which is given as, that angle each vertex is given by the 60 degree, and if we rotate this symmetry or this equilateral triangle by through the rotation of 120 degree, and we have to know that, or we have get an result, so that overall symmetry which it does not unchanged or invariant structure takes place. Again, see in the mirror plane symmetry that have the idea. So that in rotational symmetry give the idea, so that rotation for 120 degree, or that triangle which is rotated by the 120 degree, and it is carried out into itself, that side which is coincide with other first original side, and that three times at the position. If we consider that total symmetry which is given by rotation angle which is 360 degree, and if we rotate that structure by 120 degree, 240 degree and 360 degree, and we have to see the structure that it doesn't any change for this symmetry. So and by this information, that given the formula which is given by the fold number formula, and which is given by 2 pi upon the minimum angle which is rotated, or simply say that that angle which is rotated by 90 degree, yeah, 120 degree, yeah, something that. So that formula which is obtained, and for example, see that equilateral triangle which have obtained threefold degeneracy. So we want to see here the rotational symmetry. This is the translational symmetry. So we want to see here the second types of the symmetry, which is the rotational symmetry. So second type of the symmetry that is given as rotational symmetry, and that rotational symmetry give one idea to understand the term of the rotational symmetry. So here consider an equilateral triangle ABC. Okay, and for example, see for last lecture, so that have triangle trajectory which is given as at the vertices at the identical atom. So consider this point A. For example, this vertex point, consider this point B, and this vertex point, that point which is the C, and each angle which is made up by the 60 degree, and we have considered that perpendicular for this vertices point to opposite point to the altitude, draw a altitude perpendicular for the opponent side, and we get idea that each altitudes we have intersect or meet a common point, and that is point which is given by O, that is centroid point, and we have considered that rotation which is given by 120 degree, and we consider the point, for example, this point which is considered is the point P, next point which is considered point Q, and this point is considered point R, and if we rotate this symmetry on through by the 120 degree angle, or which is considered as the rotation through 120 degree. So rotation through 120 degree. So what happens here? So that equilateral triangle which is rotate by the 120 degree. So what happens where? So that vertices point at the corner, each corner for the identical atom situated is there. So consider rotation by 120 degree, this A point going to for this side, correct, and this B point which is coming for this point, and this C point which is coming for this point, and this vertices also changes the side which is also given here, and this point which is considered as PQR. So what happens? Only this vertices point which is change, okay, change the position, but whatever phenomena and whatever symmetry is there, that symmetry is as it is. So that consider this rotation which is considered as integral multiple of 120, that is considered as the rotation. So consider as rotation which is given by 120 degree, 240 degree, and 360 degree, correct. So that three types of rotation which is comes is there. So that's why we say that that symmetry which is the threefold symmetry, which is considered as the threefold symmetry, and we want to see that how actually obtain this symmetry number. So we want to here or given the formula which is the fold number which is given by, and we want to write this formula, the fold number. The formula, that is fold number, which is given here. The formula which is given, the fold number, that equal to fold number is equal to 2 pi divide 2 pi divided by minimum angle of rotation. minimum angle, that angle should be non-zero angle, that minimum angle that is non-zero of rotated which leaves of rotated which leaves the structure unchanged. The structure unchanged. So this formula which is given as the fold number, and that for example the equilateral triangle possesses three fold rotational axis of symmetry. The equilateral triangle possesses three-fold axis rotation symmetry. Okay, so for example is given here, so that fold number which is obtained by, okay, so 2 pi, for pi value which is given by 180, and given that minimum angle which is rotated by 120 degree, so that 0 is get cancelled. So if divided by this, that is 2 6 is 12, 2 9 is 18, after that 2 3 is 6, or 2 1 is 1, so that is, or 3 3 is 9, so 3 3 is 9, so that is given by answer which is 3. That's why this equilateral triangle having get the value which is threefold symmetry. Okay, so for example consider if any structure consider as taken cube or square, and which is rotating by 90 degree, 120 degree, or 240 degree. So for example consider this is cube structure. Okay, and this cube structure, this is at the vertices point have the identical atom which is situated, and if we want that symmetry which is taken by rotation which is given by at theta is equal to consider taken 90 degree. So what happens here, the fold number, that is fold number which is given by 2 into that pi value is 180, and that rotation, that minimum angle which is given by 90 degree. So that 9 1 is 9, 9 2 is 180, and 2 to the 4, so that number which is given has 4. So that symmetry which is given by four-fold degeneracy, symmetry, and that we have to consider that one-fold symmetry, two-fold symmetry, three-fold symmetry, and six-fold symmetry. That five-fold symmetry which it does not occur in the crystal structure. For example, so that the cube which is rotated by the vertical axis at the angle of 360 degree, so there are total 4 position that cube which are the coincident and with its original position, and when the cube which is rotated by the 90 degree, and that new position which is totally completely identical condition. So that I am say that your rotation angle which is considered as the 90 degree, and that 90 degree and if we want to that cube which is comes to the its original position, so that's why we want to rotate by 90 degrees its cube by 4 times. That's why we want to say that this is the four-fold symmetry. And again, next example we have to consider that which is cube which is rotated by the 120 degree, and that the new position exactly same as the original position. And if we consider that cube which is rotated by 120 degree, so how much times we rotate this cube that comes to original position, that 120 plus 120 as 240 plus as 120 that is given by the 360. So that's rotate this symmetry by 3 times, that's 1. That's why we want to say that that cube have the 3-fold degeneracy. So that is the basic idea for this rotational symmetry, and we get that clear idea. Now next type of symmetry which is see here, symmetry under the mirror reflection. But before starting that point, we want to see in the rotational symmetry, so that is how the four-fold degeneracy which is obtained, what theta is equal to what angle, and how three-fold degeneracy which is obtained, and two-fold degeneracy which is obtained. So we want to see by schematic diagram which is schematically. Okay, so we want to see here, for example, the cube structure which is given by uh, this type. Okay, and this cube structure which is rotated by 90 degree, which is rotated by the 90 degree, and at the corner, that vertices point, that identical atom which is situated, and this rotation by 90 degree. Okay, so the if take that theta is equal to 90 degree, that fold number which is for example that fold number which is given by 2 into 180 divided by 90, so that is given by number 4, and that's why we want to say that that is four-fold rotation axis. That first figure which is given as four-fold rotation axis. Okay, and if this cube which is rotated by 120 degree, so how it is structure look like? So we have to know that that default rotation direction which is anti-clockwise, and if we see this cube which is rotated by 120 degree, so fold number which is given by 2 into 180 divided by 120, so that is given by, so that is this 0 get cancel, 6 9 and again 2 on the 2, 2 3 the 6, so 2 3 the 6, and that 3 get cancelled, at remaining 3, so that the symmetry which is given by uh, three-fold rotation. Three-fold rotation. So this is idea. And if we see this cube which is rotated by 180 degree, this cube rotated by 180 degree, okay, that theta is equal to 180 degree. So that fold number which is given by 2 into 180 divided by 180, so that is given by 2 fold axis rotation. So this idea which is get clear by that minimum angle which is non-zero, which is used by rotation, so that symmetry which is given by four-fold symmetry, या two-fold symmetry, या what type of symmetry, that idea which is given. Next type of symmetry which is given as the mirror symmetry under mirror reflection. This is third type of the symmetry which is symmetry under mirror reflection. Symmetry under mirror reflection, and we have to see that, for example, consider as the equilateral triangle which is given. Consider as the equilateral triangle, that triangle which is say that is triangle ABC. Triangle consider triangle ABC, and this figure which is given by the equilateral triangle ABC. So that vertices point, that identical lattice point or lattice identical atom which is given is there, and we have to see that. So at this altitude point which is perpendicular to this plane, so consider as, for example, which is mirror which is said to be as the perpendicular to this plane. So consider that this side which is shown in mirror which is exactly coincide for this original side, and that is say that the consider that equilateral triangle, that ABC, that show in the figure, and that we fold the figure about the line at the perpendicular to altitude, and consider this point which is considered as the BP point, and see that which is exactly see in the original or half of the points of the coincide of this. So this is known as the symmetry under the mirror reflection. And if we see that cubical crystal can cut into two equal part, so that's why we have to say that is two exactly mirror part of there. So for example, consider as one of the cube which is taken, and if we cut center of this point, so that exactly two mirror part of this, and that's why we have to say that this is symmetry under mirror reflection. So for example, this is a cube structure, okay, and that Okay, so consider as this is cube. Okay, and if we cut at the exactly center part of this, okay, center part of this cube, so that exactly two same part, two equal distance or equisize same part which are formed by this, so that we have to say that which is the symmetry under the mirror reflection. So that type, or for example we want to consider this cut which is the vertical side, so that is given by this cube. Okay, first which is taken for the horizontal cut. If we cut for example this vertical way, okay, so that exactly two equal part get formed, so that is known by this. So that's why, or we want to call that is the plane of the symmetry. Or for example consider as this cube in this way. Okay, and if we want to cut this as this type of the passion at the center, so again that cube which is same cut in the two ways, so that is known as the plane of the symmetry in the rotational symmetry. Okay, so that is under the effect of the symmetry under the mirror reflection. Now next symmetry which is given as the inversion through a point or center of symmetry. So next type of symmetry that is given as inversion through a point. So that is the fourth point of symmetry, that is given as inversion through a point, or consider as or center of symmetry. So in this type of symmetry what happens, so for example the center of symmetry is also known as the center of inversion, and that point of the crystal such that the line which is drawn for any point on the crystal through this point and produces an equal distance on the other side point, and this is of the center that meets that two rays, that is known as the center of symmetry or inversion of symmetry. For example consider a center circle. Consider this is center, or for example this is considered as the two axis which is equal distance, so that is x-axis and y-axis, and this is for example center part which is denoted by O. And consider we have to taken that 2 points taken on circle. For example this point which is given as A point, and this point which is considered as the B point. Okay, and if we connect this ray, if we connect by line these 2 point, so consider for this point and this point which are connected by the line, and we have to say that distance. So for example consider as the radius of this which is considered as r, and this point to this which is considered as R. Suppose for example consider join two part, this center to this A, that is considered as the ray OA, and this part is the ray OB, and connected this whole part, so that separate this circle into two identical part, separate this circle into two identical part with the help of this centroid point O. That's why we want to say that this is the inversion symmetry or center of symmetry. For example, consider that identical part of the, taken the example of the cube. Okay, and this cube point which is given by this way. Okay, this is the cube structure, and if we see that is the central part of this cube, which is the O, and if we taken point of this or face on the cube, which is considered as the C point, and if we see or if we take the next point on this face part of this cube, which is considered as D, and if we connect this both point by the line OC or OD, or consider for example this point or this point, so what happens here? So that two identical part of the cube or a circle which is formed, which is developed, and this point of symmetry which is considered as the inversion through a point or the center of symmetry. Okay, next point of symmetry which is consider or say that the screw symmetry. Okay, and that screw symmetry that consider as the operation which is considered due to the compound symmetry operation, namely translational symmetry as well as rotational symmetry applied successively, that is known as the screw operation. And for example consider here, so for example consider in this screw symmetry that operation taken place by rotational symmetry as well as translational symmetry. So what happens here? So for example consider one identical cylinder which is given. Okay, one identical cylinder which is given, and taken that the vertices point for the alternately. So for example first point is here. Okay, second point, suppose vertex point taken is here, now next point is here, and similarly alternate fashion. Okay, and this vertices point alternate on this cylinder. Okay, and what happens when in this symmetry, if we translate and rotate this cylinder, okay, so this structure goes for in this way, so that vertex point, what happens in rotate? For example this vertex point is on side, on the upside, so what happens here, that by the rotational symmetry this point which is given here below. Again next, for this is the alternate vertices point come on the face of this cylinder, and that's why we have to say that this is the screw symmetry. Next symmetry we have considered here, that is the glide plane symmetry, and that glide plane symmetry which is considered as when a mirror plane which is combined with a simultaneous translation operation in the crystal on the glide side, and this glide plane in the crystal is always to parallel in the mirror plane, and that this type of symmetry which is considered as the glide plane symmetry. So for example, consider a plane. So new type of the symmetry which is considered as the glide plane symmetry. Glide plane symmetry, or in this glide plane symmetry which is considered as uh, a plane which is taken and the mirror sides which is also taken. So given this is plane, and this glide plane symmetry that combine the simultaneous translation operation by a crystal. So for example, taken for this lattice point to this, so that parallel of this mirror plane which is observed is there, or translational symmetry of the mirror like which is observed is here. So that's why the glide plane surface which is obtained is here, and that's why we have to say that this is the glide plane symmetry. Okay, so that once again say that what is glide plane symmetry, that when a mirror which is combined with a simultaneous translation operation in a crystal, that one glide plane and glide plane in a crystal which is always parallel to mirror plane, and this type of symmetry which is compound operation that leaves the structure which is invariant or unchanged, and that structure which is also known as the glide plane symmetry. So these are the different types of the symmetry which is commonly occur, that is translational symmetry, rotational symmetry, center of symmetry, skew symmetry, glide plane symmetry. So this is the detailed idea. We want to see that next lecture, that point is the different points of the lattice that is considered as the Bravais lattice, and that lattice which is considered as oblique lattice, hexagonal lattice, rectangular lattice, and what is the condition of the sides A and B, and what is the angle which is theta, which is or this is variant or invariant. So that is point which is see in the next lecture. So thanking of you.